We were dealing with the first law of thermodynamics, the conservation of energy, and we discussed the various forms of energy. We would have potential energy, kinetic energy, internal energy, work, and heat. And so what this section deals with are the various forms of heat that we might have. Heat can transfer from one region to another region by three modes. We have conduction of heat, radiation, and convection. Those are the only three modes for which heat transfer can occur. Conduction heat transfer deals mostly with the transfer of heat through solids, and it's through solids by dealing with the energy of the particles as they are bouncing back and forth. And certainly areas of higher energy, higher heat will impact and pass that energy to lower areas of energy. The time rate of energy transfer is referred as the Fourier's law. And Fourier's law states that the quantity of heat, Q, is going to be balanced by the thermal conductivity, which is an empirically measured parameter, times the area and the change in temperature in the direction of heat transfer. Frequently, you see the heat as a value of Q, which is uppercase Q divided by the area, and that would be equal to minus K dt dx. Frequently, we deal with the heat as lowercase q. That is, we might have, Q dot, which would be equal to the quantity of heat per unit area, and that would be our minus K dt dx in this situation. If the heat transfer is relatively uniform through the material, we can estimate or approximate the dt dx as the temperature at one end relative to the temperature at the other end divided by that length. So in that form, you could see that for the previous example of the house, we would have this as our governing equation. And if we have T1 at a higher temperature than T2, then our value of the change in temperature with respect to X will be less than 0. And that negative value there, coupled with this value, would then state that heat was traveling in the direction of the length measurement. That is, the heat was traveling in this direction. Radiation is another method for which we can have heat transfer. Once again, we've got conduction, radiation, and convection. However, this course of thermodynamics does not really deal with studying each of these independent forms. That's what your ES 3003 heat transfer will give you. Rather, in this area, I am just trying to present what the three areas of heat transfer are. With radiation, it deals with electromagnetic wave propagation. Therefore, it can occur even within a vacuum. It does not require intermediate materials. And the quantity of heat leaving, let's say, a hot surface, as shown in this figure, going to a cooler surface that might be this hemispheric dome, would be the temperature of the hot body to the fourth power less the temperature of the cold body to the fourth power. And the third form of heat transfer is convection, which usually occurs between a gas or a liquid. It does not occur within a solid. So in this schematic, if you take a look at it, we've got, a plate at a temperature T sub B for the temperature of the body, and we assume that that T sub B is greater than the temperature of the flowing fluid. So that flowing fluid, which might be air, will cool off that plate. And as it does, the direction of heat transfer will go from the hot area through the fluid in this direction.